Hey everyone, today I'm going to be covering the wonderful world of the Windows API through my talk, OwOwning with the Windows API. A little bit of small background on myself first. I go by Dijit. I also go by the handle Secretary Online. Some of my hobbies include my fascination with the color purple, programming, video games, and of course hacking. My current day job, I work as an offensive security engineer, and I focus on specifically Windows security. So let's get into the overview of what I'm going to cover today. So what is this talk about? This talk is going to cover two interesting Windows API techniques. The first one is parent process spoofing, and the second one is shellcode injection. And that will be using some interesting and undocumented functions to achieve this. I'm going to cover today the code, the execution, and any detection or prevention methodologies for each example. After that, I'm going to talk about any lessons learned and anything that I have discovered throughout this journey. So you might be asking, why do I do stuff like this? Well, I love to hack it forward and pass some of the knowledge that I've gained onto the community. It also helps document and explain some undocumented, unknown, or unexplored functions or technologies, and helps introduce new resources for red teamers, blue teamers, or any kind of security engineers. For the offensive and red teaming side, I deploy a lot of these to help learn defensive evasion techniques. On the defensive or blue side, a lot of these are to give some blue teamers insight and knowledge into some of the ways red teams work. So what are you going to expect during this talk? The first one is Golang. Golang is the language that I'll be using today for these examples. You're also getting some learning into the Windows API, along with the Golang code that is used to call it. The code examples that I'm going to be using today and the running examples that I'm going to be showing you today are actually located at my GitHub that is active and live right now at the following links below. And if you're like me, hopefully you'll find this stuff fun and exciting. So why use Golang for this? Golang is a very simple, easy to learn language that actually has a great formatting. It's compiled statically, so there's no need to install additional dependencies, and you can compile it for every single platform available. Golang also provides some easy ways to call native syscalls and Windows API functions. Also, the Golang library is written in Go, so if you want to know how a function actually works, you can dive into the source code and get a more in-depth view of how things work under the hood. Lastly, just look at the cute little mascot they have. If you're not familiar with the Windows API is a huge collection of utility functions that are used to interface with the operating system. They're very powerful, and they include some ones that include memory, privilege, and even permission management. And there are some interesting, sometimes undocumented functions that can perform some really cool and neat tricks. Some of these functions have special name prefixes, which can include NT, KW, or ZW. These prefixes may indicate that they are low-level or kernel-level functions. Why I mention this is this will be important later in one of our examples. Using the API with Go is actually very straightforward. It implies three specific steps. The first one is loading the DLL. The second one is getting the function address from the DLL using the function name. And lastly, we just execute our function. There is a Windows package provided by Go that assists with some of the basic and simple API level calls in Windows, and also provides Golang-based structs that mirror some of the C structs that Windows uses. Lastly, Golang provides also an unsafe package that is useful for memory management and converting some Golang-based pointers into pointers that can be used outside, such as Windows API calls. So this is an example of Golang code calling a Windows API function, specifically the message box function. It takes about 5 lines of code, and as you can see here on my first 2 lines, I'm just loading the DLL into memory, and I'm getting the function address of message box W from this DLL. The second 2 lines, I am just converting these strings, these Golang strings, into UTF-16 string pointers. UTF-16 string pointers are the actual ways in the Windows API you would pass strings around. Once I've done all that, I just call my function with the correct arguments, and if everything works successfully, you should see a message box that pops up like the one on the right-hand side. So let's dive into the first technique, parent process spoofing. Giving you a little bit of background, all processes in Windows have a parent-child relationship with the creating process. This relationship will show who launched who, what launched what, and what was executed by what. On Windows, there's not many native tools besides WMI and PowerShell that can view these process relationships. Microsoft does release a tool in sysinternals called Process Explorer that does a great job of visualizing these process relationships. Newly spawned processes will also inherit any access rights or any privileges that are passed down by their parent processes. And these relationships are important as it can be used for tools or utilities to determine and detect malicious actions. It can also be used for analytic-based actions that want to determine malicious actions via heuristics. There are many ways to actually spoof parent processes, but they are difficult and require some actions that can actually be detected. One of the more common spoofing methods involves overriding the PEB block or the process environment block. And this requires suspending and unsuspending or resuming the process, which can be flagged as suspicious, can be logged, and can get your actions blocked. This method I'm covering today actually does not involve any of these techniques, is less difficult to implement, and it is actually very harder to detect. So you might ask, how is this done? We're going to be using a documented feature of create process that is not well understood and contains some issues and some complications that I will address later. The new parameter was introduced with Windows Vista due to the addition of user account control. This was added to make sure user account control properly respects the parent-child relationships when launching new processes, while also respecting the new privilege separation that UAC provides. So let's get into some of how UAC actually does this. So when you click an installer that requires elevated access rights, or UAC, UAC is going to pop up. Formerly, UAC was under consent.exe. Once you click yes or accept the UAC prompt, UAC will then trigger the launch of the executable. Now, when you notice your process tree, the executable is not under UAC anymore. It is said to be started by the calling process. In our example here, it's explorer.exe. This is due to UAC spoofing the parent process relationship. If we did not have spoofing, this is the actual process, what the process tree would look like. UAC would be the parent of our installer, and Explorer would be the parent of UAC. So let's go more into depth of this. First, we're going to use the startup info ex struct to accomplish this. Startup info ex contains an attribute that is created by a function called initialize proc thread attribute list, and we're going to update that using a function called update proc thread attribute. We will use the latter function to update the attribute list with a pointer to our target process handle, and then we're going to pass our newly created startup info ex structure to our create process function. The interesting thing to note is this attribute list is actually called an opaque structure by Microsoft. It has no documentation, and it actually makes debugging very difficult, as I have to dig through raw memory just to understand what's going on and if anything's gone wrong. So let's kind of get an example of how this would work. Say we have our exe, malware exe, very aptly named, and we have our target exe. So we want to spoof under target exe. So first, we're going to open a process to our target using the open process function. Then we're going to initialize and create a new startup info ex structure. Then we're going to call initialize proc.attribute list to first initialize and generate that attribute list in memory. Then we're going to update that newly generated attribute list with a pointer to our target process handle using update proc thread attribute. Once that is complete, we're going to pass our newly generated startup info EX to create process with a flag called extended startup info EX present. Once it's complete, we should now get a process under our control that is said to be started by target.exe. And as you can see, it'll be just like the process tree located on the right-hand side. So let's get into how this looks in Golang code. First, we're actually going to initialize some of our constants that we're going to use. Basically, these are the access rights we're going to request when calling open process. Then we're going to load our DLL function from kernel32 DLL, which contains all the functions that we need. We're going to load all these functions by name, which is create process, update proc thread attribute list, and initialize proc thread attribute list. Then, this is actually simple. We're just going to open our target process by its PID with our requested access rights that we saw above in the previous slide. Then, this is where we actually create our startup info EX struct, and we initialize it using initialize proc thread attribute list. Now, we're going to update this new attribute list using update proc thread attribute with the pointer to our target handle that we got a couple slides ago. Lastly, once we convert our command that we want to run from a Golang string to a UTF-16 string pointer, we are then going to call create process with all our parameters that we need, including our startup info EX struct and the flag create new console. One of the interesting takeaways of this as well that you see in this example is you actually have to include the create new console flag in creating a process under a spoof parent, as without this flag, your process actually could crash. And I will get into this a little bit later on. So let's kind of give an example of how this looks like in action. For this example, I'm going to test against 3 separate processes. So just to show you, I am running with the most latest current version of Windows 10, and Windows Defender is fully enabled. The first process I'm going to test against is runtimebroker.exe, and I'm going to run a simple ping command just to prove that I have the ability to execute code under this command, or under this process. So as you can see, ping.exe was launched under runtimebroker.exe. Now let's target another process, dlhost.exe. And as you can see, our ping command was executed, and we have full standard output and standard error from our created process. Lastly, just for fun, let's target security health host exe. And just to show, we've created all our processes and everything functions completely without being blocked. Now, let's get into what happens when we dive in deeper with process elevation. Processes that are spoofed, like I said before, gain the same access rights and privileges as their parents. Now, because of this restriction, you can only target processes that are created by you or that you own. This is important when starting or trying to spoof processes. This also relates to processes that are created with a higher integrity level than your current process you're running in. Now, this restriction even includes processes that are elevated, and elevated processes cannot target processes that are running under the system user. However, there is one exception to this rule. There is a privilege in Windows called sdebug privilege, and if you assign this flag, this will bypass that restriction on opening processes that are running as a system. Now, this privilege flag does require elevated or admin access rights to assign. However, once you have this right, you can now run processes from an administrative command prompt to running processes under system-level processes, which will run under the system account. How we do this actually only requires 3 Windows function calls, and they're actually very well documented by Microsoft. So to kind of give a short example of how this works, we have our, again, applet name process malware.exe, and we want to open a handle to winlogin.exe. Winlogin.exe will always be running under system. So first, we're going to open a handle to our own process using open process token. Next, we are going to look up the security identifier of the SE debug privilege value by name using the lookup privilege value function. Then we're going to call the function adjust token privileges to now assign these new privileges to our process token. Once that is complete, we can go through the entire parent spoofing process again, and we now have a system level process under our control running under WinLogin exe. And the user running that will be NC Authority system. To kind of give an example on the code that powers this, it's actually very simple. It's a couple extra lines of code just needs to be added. One of the ones is we're going to load a new DLL in our code, which is adaptive32 DLL, and we're going to load only one extra function in it, which is the adjust token privileges function. And we're going to load that by name, as you can see below. Next, we're going to call lookup privilege value on the SE debug privilege string, which again, we converted into a UTF-16 string from a Go string, so we could use it with the Windows API. Then, once that is complete, we are going to tell Windows that we want to assign this token to our process by setting SE privilege enabled on one of the flag values. And then we are going to then use open process token to open our handle to our own process token. Lastly, we're going to use that newly granted token and our new privileges to assign them to our own process token. So let's go ahead and see it in action here. Now for this demo, I'm going to create 3 separate processes under system level processes. So, and as you can see again that I'm running under the current version of Windows 10 and Windows Defender is fully enabled. So I'm first going to target lsas.exe. And I'm going to run a command that's not only going to show execution, it's also going to show who I'm running under just to prove that I'm running under system. So it's going to run, and as you can see, it's running under lsas.exe, and we are now running as system. And as you can see here, when who am I in my local terminal, I'm just running as a standard user account. Now let's target winlogin.exe like our example. As you can see, our process has been created under winlogin.exe. We are still running under system, and our process is created with full standard output and standard error. Lastly, let's target servicehost.exe. And as we can see, our process is created, and we have full execution under all this process without getting blocked or picked up by any malware solutions, any anti-malware solutions. So, how do we detect this? It's actually not that easy, unfortunately. By design, this is not really considered malicious actions. It's usually considered a built-in Windows action, and antivirus products don't really care about this. There are some small methods to detect this using ETW events. However, you have to be able to filter and sort through these events, and it can also generate some false positives every time UAC is prompted for a new executable. Now, other security tools will only actually notice these spoof process relationships. Before I gave this presentation, I actually tested against a system running sysmon forwarded to Splunk to try to see if I could detect this. And as you can see, I ran cmd.exe under skype.exe. And like the log example below, Splunk and sysmon together only saw the spoof relationship, and it did not see any indicators that I was able to spoof this. Prevention may be another route we can do. We can use a flag called proc thread attribute child process policy to actually control whether or not this process can be allowed to spawn or not child processes. However, this only works in sandbox processes such as Windows app containers. So now that we got that, let's jump into our second technique, code injection. So for some background, code injection refers to allocating shellcode in a process's memory. And this could be considered local or our own memory, or remote, which is another process's memory that is not ours. Once this memory is allocated and is written to, the memory region that we wrote to can then be executed using a thread function. This injection can be used to create file lists or memory-based malware that can bypass antivirus scanners and can allow you to run less obvious or less easily detected malware samples such as Meterpreter.exe, and it's will prevent them from being detected as easily. Now, the issue, though, is while the code that you're going to be running is not as very detectable, there is some debate about the function calls that you use to execute this entire process. And it can allow for detection based on the way you do this. And I will touch on this a little bit shortly. So to get into some of how this works, there are three functions that we need to call in order for this to happen. The first one includes nallocate virtual memory, which is used to allocate a section of memory and to change the permissions on that memory segment to allow us to execute it. Next, we're going to call the function write virtual memory, which is an undocumented function call that will be used to copy our shellcode from our buffer into that newly allocated memory region. Then finally, we're going to use another undocumented function called createThreadEx, which can be used to start a thread that our shellcode is allocated in. So let's kind of get into how this would actually work. So we have our aptly named malware exe, and we want to target our process target.exe. And as you can see here on the right-hand side of our screen is our memory map of what target.exe's memory looks like. First, we're going to open a process to our target process using the function openProcess. Next, we're going to locate a section of memory in our target process using the nallocate virtual memory function. Now we have our allocated section of memory. We are then going to write our payload to that allocated section using the function write virtual memory. Finally, we're going to use the function createThreadEx to trigger the execution of our payload in the context of target.exe. And as you can see here, our payload is now executed under target.exe directly. Now, here's some of what it looks like in code. Similar to one of our previous examples, we have to request some of the access rights that we're going to be opening our process with, and we declare them above. We then load the DLL ntdll.dll, and we're going to call all the functions that we need, which only are from ntdll, coincidentally. So, firstly, we're going to call openProcess again on the process PID with our requesting rights. Next, we're going to use nallocate virtual memory to actually allocate a section of memory and store it in a pointer to our base address. Once our memory is allocated, we are going to use write virtual memory to now write the data from our buffer that contains our shellcode into the allocated memory section. Finally, we're going to call createThreadEx pointed to that new allocated section where all of our shellcode is written to now execute that in a thread. So now let's get into what it looks like when executed. The shellcode I'm going to be using for this example today is a simple exec call that is going to open Notepad. I'm going to target three separate processes. Now to show again, I am running the latest version of Windows and I am running with Windows Defender fully enabled. As of this test, it has not been detected by any antivirus solutions or Windows Defender itself. So we're going to target sihost.exe, and as you can see, Notepad.exe was launched. We are now going to target rdpclip.exe. And as we can see, Notepad.exe was launched again. Lastly, we're going to target one of the service host exe processes that are running in user mode. And as you can see, we were able to run our shellcode for each process, and we are not detected nor picked up by any antivirus solution, nor stopped. So, similar to our parent process spoofing demo, let's see what happens when we try to run it with an elevated context using the SE debug privilege flag enabled. Again, like the previous example, I am running with Windows Defender fully enabled, and I'm running on the latest version of Windows 10. So let's go ahead and target lsas.exe. So as you can see, Notepad.exe ran, however, it is not shown since it is in a separate desktop session than we are. WinLogin.exe, however, will show since it is considered our current desktop session. Lastly, we're going to target servicehost.exe, and as you can see, Notepad launched completely. We were not blocked, and we were not stopped by any anti-malware processes or Windows Defender. So let's get into detection for this code injection methodology. Detection for this is actually much better than process spoofing. Most antivirus vendors actually target the API calls that are used. So the more obscure the function calls that you use, it results in a lower detection rate for your malware. Popular EDR tools such as Carbon Black can actually be used to pick up some of these function calls and block these. Now, like I said, as this talk, it was not picked up by any tools, and I have tested multiple antivirus vendors that have been used on the client end, and they have not blocked this. So let's give some final thoughts. For apparent process spoofing, it's actually an excellent way to mask execution of your malware code or attribute process creation. The prevention of it is actually very difficult and is slim due to the configuration required. There are some drawbacks, however, for apparent process spoofing. One of them is that you have to have your binary that you want to execute on the file system. So if you do not have file system access, you can't execute this technique. Second, this can improve the ability for the defenders to perform forensic analysis on your binary, which can open you up to further detection. So this is also not good depending on how stealthy you're trying to be. Now, one of the interesting things I've noticed is the implementation of this code is difficult and it's actually very annoying. Some of the API functions that you can call actually leave you to guess the result status, including the initialize proc.attribute function, which will always return an error regardless of success status. While running spoof processes, like I stated in our code example, if you do not set create new console flag when creating the process, some processes may actually crash due to they're actually trying to access a handle to their console that is not valid. Now, the interesting thing to note is this occurs even when you supply the standard input, standard output, and standard error as valid file handles. They will still crash. So in order to execute parent process spoofing, you always need to include this flag in order to ensure that you actually have processes not crashing. For code injection, it's another great way to mask some of your malicious code, as well as code that's easily detectable. So if you want to inject Meterpreter or Mimikatz, for example, into memory. However, there's a higher chance of being detected or blocked due to the function calls that you're going to be using and the methods that are more well known of being detected. There actually is some interesting detection and prevention mechanisms that are included with Windows 10. Two of them is core isolation and memory integrity. They kind of go together. And there are some interesting features that can be used to block this from even happening on certain processes. Some of the drawbacks, however, of code injection include the detection of the function call, and also the interesting thing to note is detection from the compiled binary. If your shellcode is not obfuscated in your binary itself, antivirus can actually pick up on your binary just due to the fact that it performs a sort of strings function on it and will pick out the malicious code you have packed in there. So it's actually important to obfuscate your shellcode if you're doing a methodology such as this. So these are the references and links that I have used today. There's actually a full list of the links and references up on the README in the GitHub repo. I'd also like to thank some of the artists that I've used their art in this presentation, and they are listed below. And that's all I have today. If you have any, I will open for any questions after this. I appreciate you guys watching. If you're interested in any of my work, you can follow me on Twitter or GitHub at @SecFurry. And now I'll open for questions from the Q&A. If there is any. I will also be in the channel specifically that for the Q&A as well for any questions after this. And it seems I got a question here, what got me into the weeds in Windows? One of the things I guess I could say what got me into this specifically is Windows API calls are sometimes very obscure. And some of the ways that they're called or they're used is not really indicated by Microsoft at all. And some of the undocumented functions that people do notice are kind of interesting because some of them will either do something completely out of the ordinary or they will allow you to complete a task way more efficiently than trying to call the Microsoft standard way of doing things. For also some things I do in the offensive security line, doing like, penetration tests. It's another useful way to kind of get around some of the standard antivirus that you may have, or another way to kind of get around some detection methodologies blue teams use. It's a great way to train blue teamers on some of these techniques that, APT groups or just even your advanced run-of-the-mill hackers may be using. Sorry, another question. What is the greatest irritation that comes to securing Windows API calls? Unfortunately, you can't really secure the calls, but you can detect on them. However, the hardest thing I think would be that detecting them is difficult. A lot of tools, if they do generate notifications on API calls, there's a lot of API calls used in Windows on even the simplest things such as opening a socket or just checking for file access. That's one of the natures of why Windows is so slow on disk is you constantly have to open handles to everything you're trying to access, no matter how simple it is. So one of the interesting things I would say is that you need to be able to detect these while filtering out the kind of BS. You need to just get a notification on Windows function calls used, you actually have to create a driver package to get notifications on these. Once you do that, though, you can now get calls on certain specific function calls you subscribe to. This is actually one of the ways Carbon Black does detection on some advanced Windows API functions. So that's why antivirus vendors also detect on function calls such as create remote thread, which is a common one for code injection that is actually documented. They would just kind of fire off on this detection function call specifically. Cool. So they're going to disconnect and we're going to go to intermission. But if you guys have any questions, feel free to throw them in the Discord chat and I will get to them as you ask. Thanks for watching, guys.